All right, Unit 2, Lesson 9, side, 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 triangle congruence. So our learning goal here is let's see if we can prove one more set of conditions that guarantee that triangles are congruent and apply theorems. Okay, so triangle congruency theorems is what we're talking about. Now, in our warm-up, dare to be different, they want us to construct a triangle with the given side lengths. Okay, so like if I told you I need you to use this line segment, we'll say it's a distance of 2 or something like that. It doesn't really matter. But I know in the real world, I would give you straws. Okay, the people at Starbucks would very much be weirded out because I order, 50 some odd straws, and they're just like, what? Okay, so let's copy that. Let's paste. Let's, I don't know, let's rotate. Okay, and I'm like, you know what? I want to build a triangle. All right, let's move this over here, and then I want to get this side. Copy, paste. I want to do that right there. There we go. And then let's see. I'm gonna get this piece right here. Copy and paste. I'm gonna move that right here. And it looks like I accidentally moved one of my lines. That's probably why it's not lining up. But it would look something like that. Okay. So let's say I use that, and let me kind of polish that up there. There we go. Okay, so I'm using the sides. All right, I'm using, like, let's say this is 2, distance of 2. Okay, even though I don't really need measurements to prove this idea, and this is 5. So this is 4 here, and this is 5 here. That'd be a great example of using side, side, side. Now, if I told you, I want you to make a different triangle, but I want you to use the same exact distances. So you're like, okay, I'll use that piece there, and I'll use this piece here, and I kind of shrunk my side a little bit there, so that's gonna probably affect me later on down the road. Let me see, I'm gonna guesstimate. There we go. Actually, is there a way I can, no, I have to use 2 fingers to rotate. That's sad. Okay. Okay, so I think I got it somewhere like that. Then I'm like, okay, let's use my last piece. And I'm gonna be creative. I'm gonna make my other triangle, and I want to try to make sure it's different. The problem is come across this situation, and it looks like I'm already coming across it. All right, that's not working. Hold on. So let's see, undo. I wish I could use a grid. That'd be good. So let me see if I can redo this. Why do I feel like this is longer than it should be? So as you can see, I'm eyeballing it because I feel like I've been stretching my line segments. Okay, let's see if I can. Oh, even my finger is changing it. That's unfortunate. Okay, so there's that segment. There's that segment. And even my fingers, even though they're not stretching out, they are stretching the line itself. That's not good. Okay, so it's horrible because, as you can see, I'm having trouble tech-wise. Okay, that's a little bit better. So I'm trying to make some adjustments. So basically what I'm saying is if I give you the same three sticks or the same three pipes, and I told you to make a triangle, and then I told you, all right, I want you to make a different triangle than the one you originally created. It's not going to happen. All right, you're still just going to end up making the same triangle. I mean, the orientation may be different, but the same lengths are going to be preserved. So that's why we have side, side. All right, so here's our two pairs of sides, and then side to this side. So this is where side, side, side triangle congruency comes in. Okay, both these triangles, no matter where you build it, all right, if you're using those same three sides, doesn't matter the combination in which you build your triangle, you're still going to get the same exact result. All right, proving the side, side, side triangle congruency theorem. So we have this kid here, and they use a sequence of rigid motions to take STU, okay, onto GHJ. Okay. Given that ST is congruent to GH, okay, so let's mark these given pieces. So they say ST, right, this side, is congruent to GH, which is this side, okay. And then they say TU is congruent to HJ, so this side is congruent to this side. And segment SU, so all these sides, SU is congruent to JG. There we go. There. So for each step, explain how you know one of the vertices will line up. So we're actually going to go through this proof that this kid did, and we're just going to kind of fill in the blank, and that'll help out in getting us the logic here on why this proof will work. So ST is the same length as who? All right, and they gave us the given for that one, didn't they? They told us ST is congruent to who. So let me highlight that real quick. ST is congruent to who? Go ahead and pause the video, take a look, and okay, so hopefully you paused and you actually looked at it, and you've noticed that it should be the same length as GH. All right, so they are congruent, right? And that part was given. Therefore, there's a rigid motion that takes ST onto who? Who does ST? Because remember, this kid did a transformation to get triangle STU, right, onto triangle GHJ. So what does ST, right, what does that side map onto? Go ahead and pause the video. All right, so hopefully you pause the video and you realize ST has to go on to GH. All right, so let's look at the next part of the proof. Apply this rigid motion, it shakes triangle STU. All right, the image of T will coincide with what point? So here's point T. Who does T coincide with? Well, if you're not sure visually, all right, you can always look at the name itself, right? So that's H. So T will go to H, and the image of S will coincide with, so where does S go? So go ahead and pause the video and see where S should go. Okay, so hopefully you realize S should map onto G. So S should map over here after we do our transformation. So we go to G. Okay. So as you can see, we're going through the parts. Like all the parts are going to their corresponding parts, right? All right, so we cannot be sure of image U, which we call U prime, coincides with blank yet. So what it's saying is what? Who's U supposed to go to? So hopefully you paused and you've realized that maybe U is supposed to go to J, right? Following the pattern of the mappings. So we're pretending that we don't know for sure yet. If it does, then our origin motion takes STU to GHJ, proving that these two triangles are congruent, right? If it does not, then we conclude as follows. Okay, HJ, so this is number 4. HJ is congruent to the image of who? So take a look. Who does HJ map to? So let me highlight that. Let's use lime green. All right. Oops, that's not it. HJ. There we go. All right. So hopefully you realize that HJ needs to go to TU. All right. It's even in the name. Right. Here's HJ. Here's TU. Okay. So TU. There we go. All right. Therefore, H is equidistant from U prime and who? So go ahead and take a look. Therefore, H is equidistant from U prime and who? And hopefully you said J. Okay. So what we're saying here is if H is equidistant from U prime is basically after the sequence of rigid transformations. So maybe this kid, all right, maybe she did a translation and she got STU to be right here. U prime would be right here. Okay, so what she's saying is H right here is going to be the same distance from U prime and J. All right, given the fact that certain sides here are congruent already. All right, a similar argument shows that G is equidistant from U prime and who? So G. So here's G. It's definitely equidistant between U prime and who? Hopefully you said J. Okay. All right, GH. So this is 7. GH is the blank of segment connecting U prime and J. So GH is right here, right? And segment connecting U prime and J. U prime and J. So they're saying there's a segment here. So if you draw that segment, there we go. What is that segment? Looks like it's 90 degrees, right? Looks like this is a midpoint. Looks like these two inner parts, right? Looks like a kite now. So that's a perpendicular bisector, isn't it? Right, with GH. So that's a perpendicular bisector. So we are talking about a perpendicular bisector here. All right. And they say because the blank is determined by 2 points that are both equidistant from the endpoints of the segment. Ooh, that is very much connected to yesterday's lesson. So they're still talking about perpendicular bisector here. All right, so let's look at 8. Reflection across the blank of U prime J takes blank to blank. Well, blank if I know, because there's so many blanks. Let's try to figure out what they're talking about here. So number 8, reflect across blank of reflect across the blank of u prime j. U prime j is this line here, right? And what are they talking about? Let's see. Cross blank of uj. The line of u prime j takes, well, I know if we do a reflection, right? Like if we look here, I know if we do a reflection across u prime j, g is like way over here. H ends up like reflecting over here somewhere. So I don't think we're talking about G and H because they don't map onto each other. I know that if we reflect across GH, okay, I know that U prime is going to reflect across and map onto J, and J will reflect across and map onto U. So maybe they're talking about that. So let's see. If we reflect across, let's see. Reflect across the GH, right? Line GH. Of U prime J takes U prime to J, right? Because U prime flies over to J, vice versa. Okay, maybe. Therefore, after the reflection, all 3 pairs of vertices coincide, proving triangles. Oh, so if we do reflect across GH, G is going to stay right here. It's on the line of reflection. H is also going to stay right there. Does that make sense? All 3 vertices are still just mapping onto one another. So you actually have 2 triangles. So proving that triangle GHJ, right, and STU are congruent, right? So these 2 triangles are definitely congruent to one another because all their vertices map on. And that's what this kid was talking about with transformations. That's why we started talking about, side lengths mapping onto other side lengths, certain vertices, reflection. So it looks like we did a translation down to the right, and then we did a reflection over GH, or at least that's what the student was doing here. Okay, all right, so activity 9.3, we're proving that angle B is congruent to angle D. Well, what did they give us? Like, that's the first thing. So they tell us that this image is a parallelogram. Nice. So they gave us that. By definition, that means segment AB, ooh, they're giving us more. Segment AB is parallel to segment CD. So AB here is parallel to CD here. And segment BC is parallel to AD. Nice. Noise. Okay, good. So the definition of parallelogram, right? We should know. So first things first, right? AB, CD is a parallelogram. That was given. Okay. 2, all right. AB is parallel to CD, and AD is parallel to BC, and that's the definition of a parallelogram, or given. I mean, they flat out told us, right? So we could always say given too, if you really wanted to. 3, parallelograms, isn't AB going to be congruent to DC, right? So why? Why is AB going to be congruent to DC or CD? Okay, because that's the definition of a parallelogram, right? So definition of parallelogram means that the opposite sides are going to be congruent. Can you say the same thing about any other line segments? You can. You can say that AD and BC are also congruent, and for the same reason. It's the definition of a parallelogram. Okay. Oh, whoa. Do you guys notice that gave me a side? That gave me a side. Okay. What else? Tell you what. Is there a segment, line segment, that both of these two triangles are sharing? Hopefully you realize. AC. Right? So AC is congruent to itself. And what reason is that again? When two figures share the same side? Reflexive property. Okay. We finally have, right, side, 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 triangle congruency theorem. So 6, these two triangles, we'll call it triangle ACB, or I'm sorry, ACD, and triangle, let's see, triangle CAB are congruent by side, 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 triangle congruency. All right. But that's not what we were trying to prove, right? We are trying to prove that angle A is congruent to angle D. Well, now that we know these two triangles are congruent to one another, right? So again, we're trying to prove angle B and angle D are congruent. So we're trying to prove this angle here are congruent. Well, we just proved that the two triangles that these two angles are on are congruent to each other. So if both these triangles are congruent to each other, we know, what do we know about all their parts? They also are congruent, right? So angle B and angle D are congruent, right, by CPC/TC, which remember that means corresponding parts, congruent triangles are congruent. Okay. And that is the end of our proof. All right, we just now proved it. So first things first, what parts do we have to compare the two triangles, right? And we ended up getting 3 sides. That's side, side, side triangle congruency. That proves that these two triangles are congruent. Therefore, all their parts have to be congruent, and the parts that we're trying to prove that were congruent are angle A and angle B and angle D. Dunsies. Okay, so in summary, as long as you have 3 pairs of corresponding sides that are congruent, those triangles have to be congruent to each other. So if this side is congruent to this side, if this side is congruent to that side, those are 2 pairs so far, and this side is congruent to that side, you have 3 pairs of sides that are congruent to each other. Congratulations, that's side, side, side triangle congruency. Therefore, those 2 triangles have to be congruent to one another. Okay, have a beautiful day, and thank you.